So 2.7, we're going to learn about graphing absolute value functions. So we're going to graph our parent function, which is this absolute value of x. So we're going to graph just by plugging in numbers for x, getting values for y, and then plotting our points. So remember, this is your x-axis, this is your y-axis. So the first number, you're going to move left to right. The next one, you're going to go up or down. So first thing I'm going to do is plug in -3. What's the absolute value of -3? +3. So on our graph, we're going to go to the left to -3 and then up to +3. And that's our first point. Next, we're going to plug in -1. What's the absolute value of -1? +1. So I'm going to go to the left to -1, up to +1. Next, I'm going to plug in 0. What's the absolute value of 0? 0. So my point's going to be 0, 0. Now I'm going to plug in 1. What's the absolute value of 1? 1. So go to the right 1, up 1. And lastly, I'm going to plug in 3. What's the absolute value of 3? 3. So go to the right 3, up 3. And then just connect the dots. And this is my absolute value graph. Every single absolute value graph has this V shape. This is our parent function. Any transformation that happens to this, we keep the same shape, just apply that transformation. So we're either going to shift it to the left or right, move it up or down, stretch it, compress it, reflect it, all those things that we learned in 2.6. Any questions here? The next one says, what is the graph of the absolute value function y is equal to absolute value of x minus 4? How is the graph different from the graph of the parent function? So remembering our transformations that we learned Friday and that we practiced yesterday, what is this minus 4 on the outside going to do to our graph? It moves it down 4. So let's plug in all of our values for x and get numbers for y and see what that does when we plug them in. So we have the absolute value of -3 minus 4. What's the absolute value of -3? 3. And what's 3 minus 4? -1. So I'm going to go to the left to -3, down to -1. There's my first point. Now I'm going to plug in -1. So I have the absolute value of -1 minus 4. What's the absolute value of -1? 1. And what's 1 minus 4? -3. So go to the left to -1, down to -3. Then I plug in 0. What's the absolute value of 0?
0.
And what's 0 minus 4? -4. So stay on 0, go down to -4. Next, I have the absolute value of 1. What's the absolute value of 1? 1. And what's 1 minus 4? -3. And then I have 3. What's the absolute value of 3? 3. And what's 3 minus 4? -1. So I go to the right 3, down to -1. And then just connect my dots. That's my graph. So notice how my graph has the same shape. I just shifted it down 4, which before I even plotted my points, I knew it was just going to go down 4 because that's what transformation's happening here. All right, on the next slide, these are the same transformations that we went over in 2.6. They also apply to absolute value functions. So here we just have a specific type of function that we're looking at, but it's the same transformations. So we have, if we add or subtract on the outside, we're either going up or down. If we are subtracting on the inside, we're going to the right. If we're adding on the inside, we go to the left. If we multiply by a number greater than 1, it's a stretch. If we multiply a number in between 0 and 1, it's a compression. And then if you multiply by a negative, if it's on the outside, you have a reflection on the x-axis. If it's on the inside, it's a reflection on the y-axis.
I don't understand the.
Which of the following is the graph of y is equal to the absolute value of x plus 2 plus 3? So remembering our transformations on the last page, what does this plus 2 on the inside do to our graph?
Moves it up 2.
Left 2. And then what does the plus 3 on the outside do? Moves it up 3. So looking at our graph, if our starting point is always at the origin there, which one goes to the left 2 and up 3? D. So this, if we started our parent function here at 0, 0, we move it to the left 2 and up 3. So we just took our graph, our parent function absolute value, so that V shape. Instead of starting in the middle, we go to the left 2, because that's what this told us to do, move it to the left 2, and then go up 3. So it's the same shape, we're just taking it and shifting it.
So the pink is where it would originally.
Yeah, like the starting point is the pink
and
one.
The blue one is where it is.
Yeah.
supposed to be now. Okay.
So that blue one goes to the left 2, 1, 2, and then up 3. All right, here we're graphing again. What do you think this multiplying by 1/2 is going to do to our absolute value graph?
Make it like 50% smaller.
So, in what words from our transformations?
Compression.
A compression. So it's going to compress it. So instead of being like a normal absolute value graph like this, it's going to compress it down and make it shorter and chunkier. So this would be like a compression. An example of a stretch, so if we multiplied by a number greater than 1, would make it taller and skinnier, so it would be like that. So this would be a stretch. So just think like compressing, you're compressing it down, stretching, you're stretching it up. So here we have a compression. I'm going to pick different numbers to plug in because I don't like these. I'm going to keep 0, but I want to plug in -2 and +2. So -2, 0, and +2. So I just picked different numbers because I like them better. So if I have 1/2 times,
Pick numbers.
yeah, I'll show you on the homework. You can pick whatever values you want because you'll have to do these on the homework, but I'll talk about that at the end. So what's the absolute value of -2? 2. So what's 1/2 times 2? 1. So this would be like 2 over 2, which is 1. So I'm going to go to the left to -2 and up to +1. And then I plug in 0. So 1/2 times the absolute value of 0. What's the absolute value of 0? And what's 1/2 times 0? 0. So I plugged in 0 and got 0, so there's my second point. And then I'm going to plug in 2. So I have 1/2 times the absolute value of 2, which is 1/2 times 2, which is 2 over 2, so that is 1. So I go to the right 2 and up to 1. And then I just connect my dots. So if you look at the graph from the first slide, or I guess slide number 2, but that first example that we did, and this graph, it's the same shape, but it's just shorter and chunkier, I guess. It was just compressed down. So it's that same shape as the first graph, just compressed. All right, so next we're going to look at the general form of our absolute value function. So there's a lot on this page, but once we start to do examples, it'll be easier and you'll see it a little bit better. So this is our general form of the equation. We are going to have to identify our vertex and the axis of symmetry, which in our graph, so if I have a graph here, my absolute value graph, the base, so where the bottom part is, that sharp corner, that is my vertex. And then if I drew a dotted line right down the middle, let's change the color so we can see. Kind of, you can see that orange line down the middle. That is my axis of symmetry. So the axis of symmetry cuts the graph in half into two equal parts. So it's symmetrical on that line. So symmetrical meaning the left side's the same exact thing as the right side. And then our vertex is just that sharp corner there, that base of your graph. So to find out what our vertex is, that comes from the h and k in our graph. So what we're adding on the inside is our h, and what we're adding on the outside is our k. So our vertex is just h, comma, k. And whenever we plug in our h into our vertex, we have to change the sign of h. So you always change the sign of h. If in your equation here you had x plus 4, that would mean our h is negative 4. So you always change the sign of h. And then your axis of symmetry repeats whatever that h value is. So it's x is equal to whatever h is. So you'll get x is equal to some number, but it's always that h. All right, the next example says, without graphing, what are the vertex and axis of symmetry of the graph, and how is the parent function transformed? So first thing we can do is identify our transformations. What does this 3 being multiplied on the outside do? It stretches it. What about this minus 2 on the inside? It goes to the right 2. And then plus 4 on the outside? Up 4. So those are 3 transformations that are happening here. Next thing I want to do is identify my vertex and the axis of symmetry. So my vertex comes from that h and k. So in my general form, I have y is equal to a times absolute value minus h plus k. So what is in that h position? Negative 2, but remember you always have to change the sign of h. So what's your h?
2.
Positive 2. And then what's in that k position? 4. So my vertex is 2, 4. And then what's my axis of symmetry? So it's x is equal to h, and what's my h? 2. Because remember, your vertex is h, k, so your h is 2. So that 3 really doesn't mean anything. It's not involved in our vertex or axis of symmetry. It's just telling us we have a stretch, but it doesn't apply to the vertex or axis of symmetry. The only thing we care about in our vertex is h and k. And then when you write your axis of symmetry, you have to make sure you have that x is equal to. You can't just put 2. Do you guys have any questions here?
So it won't be negative 2.
All right, the next slide we're doing the same thing. First, let's identify our vertex and axis of symmetry. What's our vertex?
1.
So 1 and 4, but we have to change the sign of 1 because you always change the sign of your h. So it would be negative 1, 4. So that's our h and our k. So remember, you always change the sign of your h. And then our axis of symmetry would be what?
Negative 1.
X is equal to negative 1. Can't forget that x is equal to. Now we can identify our transformation. So we have plus 1 on the inside does what? Moves it left 1. What about plus 4 on the outside? Up 4. What about multiplying by 1/3? Compression. And then what about multiplying it by a negative? A reflection. Awesome. Is it a reflection on the x-axis or the y-axis? X, because you keep your x's outside your house. In the next example, all we have to do is find the vertex and axis of symmetry. So what would our vertex be? Awesome. The 4 comes from the inside, so we always have to change the sign of h, so it would be -4, and then k stays the same, so -3. And what's our axis of symmetry? X equal to -4. Perfect. It always repeats that first number. This one doesn't ask us to identify the transformations, but just for extra practice, let's do it. So what does this 2 do to our graph? Stretch. What about this plus 4? Left 4. And then -3? Down 3. Yes. So for the next one, it says determine if the function is a vertical stretch or vertical compression. So when we multiply by 2/3, is it stretch or compression?
It's a stretch.
It's a stretch because, why do you think it's a stretch?
It's over 1.
Because 3 halves is greater than 1. Because 3 halves is like saying 1.5, right? Greater than 1. So it's a stretch. So even though it's a fraction, it's greater than 1.
So does that mean always when it's improper fraction it's most likely?
Because it would be bigger than 1, so yes. Ella, what do you think for the last one? 7 halves, is it a stretch or compression?
Compression. It's a compression.
You had it right the first time. It's a stretch because 7 halves is greater than 1. The negative makes it a reflection.
I thought it was okay.